Good day! Today we will continue our discussion of the concept of virtual memory and paging. Before that, let's see what we have covered so far. We've covered the notion of an address space, memory swapping, managing free memory, overlays as an approach to virtual memory, and page and page table structure. Today we will talk about paging algorithms and the design issues of paging and the memory systems in general. When a page fault occurs, the operating system has to choose a page to evict, to make room for the incoming page. If the page to be removed has been modified while in memory, it must be rewritten to the disk to bring the disk copy up to date. If, however, the page has not been changed, the disk copy is already up to date, so no rewrite is needed. The page to be read in just overwrites the page being evicted. Let's start with the most efficient algorithm, the optimal one. Each page can be labeled with a number of instructions that will be executed before that page is first referenced. The page with the highest label should be removed. As you can see, the pages, we start to mark the instruction number during which the page was flagged. The page with the highest number is, as you can see, 6th, and it will be a page G. Thus it will be removed. But how can we predict that the page will be referenced next at the time of a page fault? In practice, not in any way. Operating system has no way of knowing when each of the pages will be referenced next. We can simulate this algorithm only on the second run with information collected during the first run. Let's now look at a not recently used algorithm. As you remember from the last chapter, each page has its own R and M bits. The main idea of this algorithm is to divide all pages into classes depending on these bits. Algorithm removes a page at random from the lowest numbered non-empty class. And as you can see in the example, pages are arriving as they are being referenced. Then we modify pages B and E and interrupt request happens. The new page comes in, and pages A, C, D, F, and G are from the lowest class 0. Then a new page comes into a page table and should evict one of these pages at random, and it is a page C. There is also such algorithm as first in, first out. The operating system maintains a list of all pages currently in memory, with the most recent arrival at the tail and the least recent arrival at the head. At the time of a page fault, the page at the head is removed and the new page added to the tail of the list. However, it is rarely used in its pure form because the oldest page might still be useful. The question arises, how can we fix this issue? The answer is second chance algorithm. It is basically the example of modified FIFO, but we also inspect the R bit of a page. Let's now see how it works on an example. Pages arrive as they are being referenced with respective load time. We start to reference some pages, and after a new page comes in, we observe the reference bit of the first page A, it is equal to 0, thus we delete the page A and put the H at the end of the queue as it was in the first in first out algorithm. Now the new page comes in and we observe the first page again. It has the reference bit equal to 1, thus the load time is changed to the time of a page fault and we put the page B at the end of the queue. And we observe the first page once again, its reference bit equal to 0, thus we just remove this page and put the J at the end of the list. Second chance is unnecessarily inefficient because it constantly moves pages around the list. So the new approach is introduced. Keep all pages in a circle list in the form of a clock with a hand pointing to the last page. So, now let's observe clock algorithm on the real example. First of all, we have pages arriving in the memory as they are being referenced, and if the new page should be swapped in, we should search for the first page with reference bit equal to 0, nullifying all pages with reference bit equal to 1. First, the page X arrives and we search for a page with reference bit equal to 1, nullifying others, and it is a page A. First, we simply swap page X with a page A. Then some pages are being referenced, and the same situations happen once again. The first 0 page is C. First, we put page Y at the place of a page C. A good approximation to the optimal algorithm is based on the observation that pages that have been heavily used in the last few instructions will probably be heavily used again soon. This idea suggests a realizable algorithm. When a page fault occurs, throw out the page that has been unused for the longest time. This strategy is called least recently used paging algorithm. Although least recently used is theoretically realizable, it is not cheap by a long shot. To fully implement least recently used, it is necessary to maintain a linked list of all pages in memory with the most recently used page at the front and the least recently used page at the rear. Finding a page in the list, deleting it, and then moving it to the front is a very time-consuming operation, even in a hardware. However, we may try to do it. We need to assign a 64-bit counter for each page table entry, automatically incremented after each instruction. After each memory reference, the current value of the counter is stored in the page table entry for the page just referenced. When a page fault occurs, the operating system examines all counters in the page table to find the lowest one. It is the one to be evicted. It is also possible to implement least recently used in a software. Let's observe these approaches. The first one is called not frequently used algorithm. It requires the software counter associated with each page initially 0. At clock interrupt, the operating system scans all the pages in memory, and for each page, the R bit, which is 0 or 1, is added to the counter. The counters roughly keep track of how often each page has been referenced. When a page fault occurs, the page with the lowest counter is chosen for replacement. The main problem with not frequently used is that it's like an elephant, it never forgets anything. If pass 1 happens to have the longest execution time of all the passes, the pages containing the code for subsequent passes may always have lower counts than the pass 1 pages. Now let's observe our algorithm on a real example. We have initially empty, free-sized page table. First of all, we reference page 1. It is not in our page table, first we get a page fault and we increase the counter of 1. The same actions happens for page 4 and for page 2. The next reference page is 4, but it is already presented in our page table. First we get a page hit and we increase the counter of page 4. Next page to be referenced is page 23, but our page table is full and we need to evict one of the pages. We search for the lowest non-zero counters and it is either page 1 or page 2. The page 1 were used longest time ago, first we choose it to evict. We simply swap page 1 with a page 23. Next page to be referenced is page 3, we again search for the lowest non-zero counters, it is either 2 or either page 23. And as we referenced the page 2 the longest time ago, we choose it to evict. And basically the same thing happens for the next reference page. The lowest counter is either 3 or page 23, where page 23 we referenced the longest time ago, first we swap it with page 2. Fortunately, a small modification to the not frequently used makes it able to simulate least recently used quite well. The modification has two parts. First, the counters are each shifted right one bit before the R bit is added in. Second, the R bit is added to the leftmost rather than the rightmost bit. Here you may see the counters for 4 pages. At the time of the first tick, page 0 and page 2 are being referenced. The counters increased accordingly. Before the next tick, counters are shifted right one bit, then the same actions are undertaken twice. As you can see in the example, the counters are increasing. In the purest form of paging, processes are started up with none of their pages in memory. As soon as the CPU tries to fetch the first instruction, it gets a page fault, causing the operation system to bring in the new page containing the first instruction. Other page faults for global variables and the stack usually follow up quickly. After a while, the process has most of the pages it needs and settles down to run with relatively few page fault. This strategy is called demand paging because pages are loaded only on demand, not in advance. Before moving to a working set algorithm, it is vital to know some definitions. The set of pages that a process is currently using is its working set. A program causing page faults every few instructions is said to be thrashing. Most of the processes exhibit a locality of reference, meaning that during any phase of the execution, the process references only a relatively small fraction of its pages. Processes are often moved to the disk. In other words, their pages are removed from memory, to let others have a turn at the CPU. The question arises of what to do when the process is brought back in again. Many paging systems try to keep the track of each process working set and make sure that it is in memory before letting the process run. This approach is called the working set model, which was presented by Denning in 1970, and it is designed to greatly reduce the page fault rate. Function v is called a working set. It says that in any instant of time t, there exists a set consisting of all the pages used by the k most recent memory references. One can come to the idea that because the one most recent references must have used all the pages used by more than one most recent references, and possibly others, function of w is a monotonically non-decreasing. And to implement working set model, it is necessary for the operating system to keep track of which pages are in the working set. Having this information also immediately leads to a possible page replacement algorithm. When a page fault occurs, find the page not in the working set and evict it. Same value of k must be chosen in advance. Then, after every memory reference, the set of pages used by the most recent k memory reference is uniquely determined. Counting back k memory references is prohibitively expensive. Well, we may use execution time instead. If a process starts running at a time t and has 40 milliseconds of CPU time at real time t plus 100, for working set purposes its time is 40 milliseconds, which is also called current virtual time. With this approximation, the working set of a process is the set of pages it has referenced during the past tau seconds of virtual time. Speaking about working set algorithm, when observing the pages, the following situations may occur. If r bit is equal to 1, we set a time of the last use to current virtual time. If r bit is equal to 0 and the difference between current virtual time and time of the last use is larger than tau, then we remove that page. But if the difference between current virtual time and time of the last use is less or equal than tau, then we remember the time of the last use of that page and store it until the end. If all pages are in the working set, the one with r equal to 0 and the greatest h is evicted. In the worst case, all pages have r equal to 1, so 1 is chosen at random for removal. Preferably a clean page if one exists. When the page fault happens, we start to search for page to evict. The first page satisfies case 1, therefore it stays in memory. The second one satisfies the case 3, thus we remember its time of last use to check at the end of the search. Another page suits case 2 as its difference between current virtual time and time of last use is bigger than tau. Thus, we simply remove it. Since we found the room for the incoming page, no other actions needed and all other pages stay in the memory. Page 2 also remains untouched. The basic working set algorithm is cumbersome, since the entire page has to be scanned at each page full until a suitable candidate is located. Well, new approach was invented: a circular list of page frames. Each its entry contains time of the last use field from a basic working set algorithm, r-bit, which is shown, and m-bit, which is not shown. It is widely used in practice since it is simple and provides good performance. And let's now observe the cases of the working set clock algorithm. If r is equal to 1, we simply set r to 0 and advance head to the next page, and the algorithm is repeated for that page. If r equal to 0, the h is h then tau and the page is clean, the page frame is simply claimed and the new page put there. If the page is dirty, it cannot be claimed immediately since no valid copy is present on the disk. To avoid the process switch, the write to the disk is scheduled, but the hand is advanced and the algorithm continues with the next page. Let's now see how it goes. The hand of a clock is advanced to the page for time 1620. The reference bit of this page is 1. We change it to 0 and the hand is advanced. The next page is dirty, has r bit equal to 0 and h is greater than tau, that's why we schedule a write to the disk. The next page, r bit is equal to 1, thus we change it to 0 and advance the hand. The next page is clean, its r bit is equal to 0 and the h is greater than tau, thus we remove it and swap with the incoming page. However, this is not enough to consider. We also need to consider what happens when a hand comes all the way around and backs to its starting point. If at least one write has been scheduled, then the hand constantly keeps moving looking for a clean page, and when it finds the first clean page, it deletes it. If no writes have been scheduled, the simplest thing to do is to claim any clean page and use it. If no clean pages exist, then a current page is chosen as a victim and written back to the disk. All in all, two best algorithms are deisgn and WS clock. They are based on least recently used and working set, respectively. Both give good paging performance and can be implemented efficiently. A few other algorithms exist, but these two are probably the most important in practice. Now, as we know the logic behind paging algorithms, it's time to get deeper understanding of how to get a good performance from a paging system. Let's go through all these topics one by one. A major issue associated with these paging algorithms is how memory should be allocated among the competing runnable processes. Suppose we have three processes A, B, and C, which make a set of runnable processes, and A gets a page fault. Should the page replacement algorithm try to find the least recently used page considering only the pages currently allocated to A, or should it consider all the pages in memory? Well, two options are possible, let's observe them one by one. Speaking about local replacement algorithm, it basically tells us, let's try to find the least recently used page considering only the pages currently allocated to A. We go through all pages of A and see that A3 has the lowest age. First we remove it and swap it with the incoming page. This is called local page replacement algorithm. However, global page replacement algorithm means that the page with the lowest age value is removed without regard to whose page it is. We cycle through all pages and find out that the page with the lowest age is C1. Thus, we simply swap it. In general, global algorithms work better, especially when the working set size can vary a lot over the lifetime of a process. If a local algorithm is used and the working set grows, thrashing will result, even if there are a sufficient number of free page frames. If a working set shrinks, local algorithms waste memory. If a global algorithm is used, the system must continually decide how many page frames to assign to each process. But we need to find a way how we can do this. Well, we actually can monitor the working set size as indicated by the agent bits, but this approach does not prevent thrashing. Working set may change size in milliseconds, whereas the agent bits are a very crude measure spread over a number of clock ticks. Another approach is to have an algorithm for allocating page frames to processes. One way is to periodically determine the number of runnable processes and allocate each process an equal share. Thus, if we will have 100 available page frames and 10 processes, each process gets 100 frames. Although this method may seem fair, it makes little sense to give equal share of a memory to 10 kilobyte process and to a 300 kilobyte process. Instead, pages can be allocated in proportion to each process total size, with 300 kilobytes process getting 30 times more than a 10 kilobyte process. It is probably wise to give each process some minimum number so that it can run no matter how small it is. If a global algorithm is used, it may be possible to start each process up with some number of pages proportional to the process size, but the allocation has to be updated dynamically as the processes run. One way to manage the allocation is to use PFF, which is called Page Fault Frequency Algorithm. It tells when to increase or decrease a process page allocation, but says nothing about which page to place on a fault. For a large class of page replacement algorithm, including least recently used, it is known that the fault rate decreases as more pages are assigned, as we've discussed previously. This is the main assumption behind the page fault frequency algorithm. It is important to note that some page replacement algorithms can work with either a local replacement policy or a global one. Least recently used and first in first out can work with both concepts. On the other hand, for other page replacement algorithms, only a local strategy makes sense. In particular, the working set and WS clock algorithms refer to some specific progress and must be applied only in that context. However, even with the best choice of algorithm and optimization, our system still might thrash. One symptom of this situation is that page fault frequency algorithm indicates that some processes need more memory, but no processes need less memory. But it's barely impossible to give all memory that processes need. The only real solution is to temporarily get rid of some processes. Our target is to know how can we do it. The simplest way is to swap processes to the disk and divide new free page frames among thrashing processes. Swapping is continued until the thrashing stops. However, another factor to consider is the degree of multiprogramming. When the number of processes in main memory is too low, the CPU may be idle for substantial periods of time. This consideration argues for considering not only process size and paging rate when deciding which processes to swap out, but also its characteristics, such as whether it's CPU bound or in input-output bound, and compare it with characteristics of other processes. Let's now take a 5 seconds break because themes are really long and you may get frustrated. We will talk about page sizes, we will talk about distributed shared memory and shared libraries concept, so be prepared. But first of all, let's talk about the page size. The page size is a parameter that can be chosen by the operating system, and determining the best page size requires balancing several competing factors, and as a result there is no overall optimum. To start with, two factors argue for a small page size. A randomly chosen text, data or text segment will not fill an integral number of pages. On the average, half of a final page will be empty. The extra space in that page is wasted. This wastage is called internal fragmentation. With n segments in memory and the page size of p bytes, NP divided by 2 bytes will be wasted on internal fragmentation. This reasoning argues for a small page size. Another argument for a small page size becomes apparent if you think about a program consisting of 8 sequential phases for 4 kilobytes each. With a 32 kilobyte page size, the program must be allocated 32 kilobytes all the time. With a page size of 4 kilobytes or smaller, it requires only 4 kilobytes at any instant. In general, a large page size will cause more wasted space to be in memory than a small page size. On the other hand, small pages use up much valuable space in the translation look-aside buffer. Say your program uses 1 megabyte of memory with a working set of 64 kilobytes. With 4 kilobytes pages, the program would occupy at least 16 entries in the TLB. With 2 megabyte pages, a single TLB entry would be sufficient. As TLB entries are critical for performance, it pays to use large pages whenever possible. Transfers to and from the disk are generally a page at a time, with most of the time being for seek and rotational delay, so that transferring a small page takes almost as much time as transferring a large page. Also, small pages mean the programs will need many pages, and thus a large page table. Having a small page size means that the time required to load the page registers gets longer as the page size gets smaller. Furthermore, the space occupied by the page table increases as the page size decreases. Let the average process size be S bytes and the page size be P bytes. Furthermore, assume that each page table entry requires E bytes. The approximate number of pages needed per process is then S divided by P. Occupying S E divided by P bytes of page table space, the wasted memory in the last page of a process due to internal fragmentation is P divided by 2. Thus, the formula for the overhead is the sum of these fractions. We know that the function is monotonic. Well, we can find its extremum. You can see the result highlighted with a red color. It is basically the optimal page size. Most computers have a single address space that holds both programs and data, as shown on the slide. However, if address space is too small, it forces programmers to stand on their heads to fit everything into the address space. One solution is to have separate address spaces for instructions and data, called I space and D space. Each address space runs from 0 to some maximum, typically 2 in the power of 16 minus 1 or 2 in the power of 32 minus 1. Each one has its own page table with its own mapping of virtual pages to physical page frames. When the hardware wants to fetch an instruction, it knows that it must use I space and the I space page table. Same things applies to D space. Other than distinction, having separate I and D spaces does not introduce any special complications for the operating system, and it does double available address space. Rather than the normal address spaces, separate I and D spaces are used nowadays to divide the L1 cache, which, as you may remember from the computer architecture course, is the fastest cache which holds variables for the CPU. In a large multi-programming system, you may have a situation when you have two copies of the same page in memory at the same time. We want to improve this situation, but we need to keep in mind that not all the pages are shareable. We should pay attention to the protection of the page table also. Well, you may already understand why we've talked about separate spaces previously. It is relatively straightforward to share programs by having two or more processes use the same page table for their I space, but different page tables for the D spaces. As you can see in the slide, our process table entries point to the same instruction space, but to the different data. However, if we will remove instructions for one process, it will result in thrashing for another process to bring these instructions back. At the time of termination of a process A, it is essential to discover which pages are still in use. Searching all the page tables to see if a page is shared is usually too expensive, so special data structures are needed to keep track of shared pages. In particular, in Unix, after a fork system call, the parent and child are required to share both program text and data. In the page system, what is often done is to give each of the processes its own page table and have both of them point to the same set of pages. Thus, no copying of pages is done at a fork time. However, all the data pages are mapped into both processes as read-only. As soon as either processes update a memory world, the violation of the read-only protection causes a trap to the operating system, so subsequent writes to either copy proceed without trapping. This approach, called copy-on-write, improves performance by reducing copying. In modern systems, there are many large libraries used by many processes. For example, multiple input, output, and graphic libraries. Statically binding all these libraries to every executable program on the disk would make them even more bloated than they already are. One may come to the idea of shared libraries, but before touching that theme, let's refresh our knowledge about static linking. Here I've presented a Linux command which links all the object files in the current directory and then scans two libraries. Any functions called in the object file but not present there are called undefined externals and are sought in the libraries. At the time of the linking, we search for called functions in the library files and merge them all together as a binary code. Well, static linkers results in wasting a huge amount of space on the disk and space in RAM. A common technique helping to solve this problem is to use shared libraries, which are called DLLs or dynamic linked libraries on Windows. When a program is linked with shared libraries, which are slightly different than static ones, instead of including the actual function called, the linker includes a small stub routine that binds to the called function at a runtime. We won't cover how this routine works in detail, but it is an important fact to know. Also, shared libraries may be loaded either when the program is loaded or when the functions in them are called for the first time. On this slide, you may see a pure difference between static and dynamic libraries. In addition to making executable files smaller and also saving space in memory, shared libraries have another important advantage. If a function in a shared library is updated to remove a bug, it is not necessary to recompile the programs that call it. The old binaries continue to work. This is a really cool advantage for commercial software. Shared libraries come with one little problem that has to be solved. The problem is illustrated in the next slide. Here we see two processes sharing a library. However, the library is located at different addresses in each process, presumably because the programs themselves are not the same size. Suppose that the first thing the process B has to do is to jump to address 16 in the library. But the library is shared, thus we are performing a jump to this area when we absolutely need another one. If the library were not shared, it could be relocated on the fly as it was loaded. One way to solve this problem is to use copy-on-write and create new pages for each process sharing the library, but this defeats the purpose of sharing the library. A better solution is to compile shared libraries with a special compiler flag telling the compiler not to produce any instructions that use absolute addresses. Code that uses only relative offsets is called position-independent code. The shared library is just a needle in a haystack. The larger concept is a memory-mapped files. Let's now talk about them. The idea of memory mapped files facility is that a process can issue a system call to map a file onto a portion of its virtual address space and uses the disk as a backend store. When the process exits or explicitly unmaps the file, all the modified pages are written back to a file of the disk. Well, as you can see in the example, a file initially stays in our disk. When we need and we want to perform some operations with this file, we turn it to the virtual address space, and then we perform some operations. As we finish operations, the information about the file is now stored on the disk. If two or more processes map onto the same file at the same time, they can communicate over shared memory. Writes done by one process to the shared memory are immediately visible when the other one reads from a part of its virtual address space mapped onto a file. If the memory mapped files are available, shared library can use this mechanism. We will basically talk about this approach later. Sometimes we may need to clean up all dirty pages in our page table so the paging will work better. That is where the paging daemon comes in handy. It is a background process that sleeps most of the time but is awakened periodically to inspect the state of memory using some algorithm. As you can see, the number of pages becoming larger and larger in our page table, and when page daemon comes at any instant of the time and tells us to write some pages back to the disk. Let's now observe how paging daemon works with the working set clock algorithm. Before or after our normal page algorithm does its work, the daemon simply searches for the dirty pages and schedules them to the disk. As you can see, the pages B and E are dirty, so we simply overwrite them on the disk, so there will be 0 modified bits for these pages in the page table. Worth mentioning that in some advanced systems, programmers have a unique ability to have control over the memory map by naming regions of their memory. And it may become possible for some processes to give another process the name of a memory region, so process will also map it in. As you can see, with this approach we also can implement a shared memory message passing system. If processes can control their page map, a message can be passed by having the sending process and map pages containing the message and the receiving process mapping them in. Here only the page name have to be copied instead of all the data. Yet another advanced memory management technique is distributed shared memory. Multiple processes share a set of pages over a network, possibly but not necessarily as a single shared linear address space. Let's now see how it works straight in the example. When a process references a page that is not currently mapped in, it gets a page fault. For example, process B says that I need this page. I keep getting page faults. Then the page fault handler, which may be in the kernel or in the user space, locates the machine holding the page and sends it a message asking it to unmap the page and send it over the network. When the page arrives, it is mapped in and the fault in instructions is restarted. You may find more information about distributed shared memory in the chapter 8 of the Tannenbaum. Well, that is basically all for today. Thank you for sharing your time with me. I hope that this lecture was useful for you.